Bit of a long title for our first presentation after the dinner of yesterday, so we're going to change it on how to use Legos for fetal ECG denoising. And I will show you why I'm talking about Legos, those bricks from Denmark that the children play with. If we look at the ECG, if we would measure the ECG, if we measure ECG from the mother, in this situation you can get these nice waveforms. You can see the P wave, QRS complex, T wave. If we measure for the fetus, as you can see, it's much more complicated. With some idea we can find some R peaks where the crosses are, more or less. You can forget about the P wave, you can forget about the T wave, although T wave is supposedly relevant for fetal monitoring, which I will mention briefly later in the presentation. But if you then think about what are the properties of ECG or fetal ECG which we could exploit for denoising, what we can think, well, as you have seen, there's excessive noise that can come from, for instance, fetal movement. Another problem is we don't have clean reference data, so we could think we could start with a neural network, we can train it towards very clean data, but we don't have clean data from the fetus. And of course you can simulate it with adult ECG, but of course we don't really know if that's true. So I'm going to present a way to train a neural network without using clean reference data. And what we are going to use is a lot of knowledge that we have, because for instance the ECG can be described in a few building blocks. I already mentioned the P wave, the QRS complex, T wave. So these are basically blocks that represent some physiological or electrophysiological activity of the heart, which we measure with the ECG. And another thing that we can use, that consecutive heartbeats of the ECG of consecutive heartbeats is very similar. It looks a lot like each other if you go back, if you look at the one of the mother. They are not identical, but they really look alike from one heartbeat to the next. And that's where Legos come in. Because we can describe this problem in terms of Legos, because these building blocks, the P wave QRS complex, they can be blocks. And how you combine these blocks together, that's basically the manual if you're going to build something, how you should stack these blocks together. And that's actually what we're going to exploit. Because if you think about the design of these blocks, what are the blocks that we need, and how do we build them towards an ECG, we can think of a well-known algorithm from signal processing. It's the ISTA algorithm, stands for iterative shrinkage and thresholding algorithm. And it's an extremely powerful denoising algorithm, because it can describe, in this case the ECG, as a combination of a few building blocks. And why it's so powerful? Because it tries to use sparsity, meaning as few building blocks as possible. And ideally that doesn't leave room to reconstruct noise, so it will only reconstruct those parts that you will see from one heartbeat to the next, and the noise should disappear. A problem with that is you need to a priori define the shape of the blocks, which is difficult because, as said, if we cannot use adult ECG to do very realistic simulations, we also don't know what these building blocks look like. But then there is learned ISTA, so it's a neural network implementation. It's basically an unfolded neural network, because ISTA is an iterative algorithm, as what the I stands for, but you can unfold the neural network and then you can expedite the training a lot. Where ISTA typically needs about 1,000 to 3,000 iterations until convergence, the learned ISTA needs about 10. So you can imagine it's much and much faster. And not only does it learn how to build the manual, so learn the sparse code, which is basically the manual how to stack these blocks together, but you can also use it to learn the shape of the blocks from the data. So you learn the manual. There's one problem then still, if you apply learned ISTA, is that for every ECG you have to create a new manual. And that doesn't seem smart, because we know that one heartbeat looks like the previous one, which looks like the previous one, etc. So if we describe that, we can say the ECG of one heartbeat, t plus 1, is almost the same as the ECG of the previous heartbeat at time t, but there are some physiological variations and there is noise. And this is actually something that we also know very well from signal processing, because we can describe this behavior as a Kalman filter, which can dynamically track all these differences and can make an estimate of which part of the difference comes from physiology and which part comes from noise. In other words, basically what we say, this manual of how to stack these Lego blocks together should be almost the same between two heartbeats. Could be that you maybe use a different color of a brick, or you place them slightly in a different way together, but it should almost be the same. So that's why we came with the proposal to do Kalman Lista, which basically means that we use that Kalman filter, so the dynamic tracking of variations, but we use that in the sparse coding domain, so in the manual of the Lego blocks. And then we combine all the information of the ISTA algorithm, which is extremely powerful. We combine information of Kalman filter, where you can track variations over time. And in the end, we have a fully machine-learned implementation, so a neural network, which we can learn from the data. It can learn the shape of the bricks, of the blocks, if you want. And then we can train it, and that's really nice. We can train it unsupervised, because the target in our training is actually going to be the next heartbeat, which is extremely noisy. But if you keep repeating that, it will at some point start to learn that that noise doesn't repeat, and those blocks do repeat and do appear. So you can train it unsupervised. Briefly, the layout of the architecture. So it is a neural network, but it's a neural network that has extremely few weights. That's also why it's so fast. For instance, this is a key element in the ISTA algorithm. It's a shrinkage operator. And we have a learnable parameter alpha, which basically describes the width of this plateau. And that's something the neural network learns from the data, and that's also why it speeds up the process so much. These other combinations, you don't have to focus too much on them. This is a layer in a neural network. This is a layer. And what you can now see, that if you look at the top part, this is the learned ISTA algorithm, and what we do every time we update it based on previous estimates from a previous heartbeat using a Kalman filter. And here's an example of how that can work. So here we can see in blue an original signal. We made it a very clean one so that you can see what it's all about. In orange is a reconstruction where we moved it by 0.5 so that they are not fully overlaid. But what you can now see, very interesting, is the sparse code. So it has learned that this signal can be reconstructed by only 3 building blocks, where one is placed here, and the shape of the block looks like this. One block is placed here, the shape is this, and as you can imagine, the last one, the T wave, shape that. But these shapes are learned by the algorithm, and the sparse code, so this manual, is also learned by the algorithm. If we then apply it to real fetal data, we did as a benchmark, this is a measured signal, so it's actually kind of nice. You can even see a fetal ECG. If you look very carefully, there is the QRS complex. As one thing what we did, we determined the median over 5 minutes. So 5 minutes, that's probably about 700, 800 heartbeats. Calculate the median, and you can see it doesn't really work. There's something there, but we cannot really see. We can also do Kalman filtering, so without the ISTA or Lista algorithm, it doesn't work. And if we apply our Kalman Lista algorithm using only 10 heartbeats preceding, this is the output that we get, which to me was very remarkable and very impressive when we got this. We actually questioned whether we made a mistake because it was too good to be true almost. But we have convinced ourselves now that it really works as we think it works, and even better, but it's really true. So some other examples of what we did to test it further, what it can do. So on the top you can again see a simulator measurement. So this is a clean ECG, the one in the middle, and we added a lot of noise. And the reconstruction is what the algorithm makes out of that noisy input signal, the simulator measurement, which I think is a very good reconstruction. In this case, is a patient with a cardiac disease. This patient has heart failure, so it can also track pathologies. And as you can imagine, of course, we're talking here about fetal monitoring or pregnancy monitoring. So one thing that has been reported and has been widely used, not so much anymore, I think, is the monitoring of the ST segment. And it has been shown in literature and extensively researched that if you track variation in the ST segment, if there's an elevation of the T wave, there is an associated with hypoxia. And we have been talking yesterday about CTG analysis, and I think it will be very difficult to solve the full puzzle with only CTG, so we're looking for extra information to complement the CTG. And why not the ECG? Because the ST segment has been proven to be relevant. There are some challenges with the implementation. One thing is, for instance, that at this moment you need the scalp electrode, so you can only use it at the very last stage when the membranes have ruptured. But I think we can also use it non-invasively. So what we did, we took a clean ECG because we wanted to see if we could track variations. And over the course of about 100 heartbeats, say less than a minute, we made quite a big increase in the T wave amplitude, as you can see here. So we started with this ECG, and basically in software and signal processing we blew up the T wave, making it bigger and bigger, just over the course of a few, well, I would say a few heartbeats. This goes faster than what you would expect in a physiological recording, where the T wave would just gradually increase. And we wanted to see whether this would work. And actually what we then saw, if we provide these inputs, so we added a lot of noise, these are the reconstructions that we find. And if we then measure the ST elevation that we can extract from this, then you can see on the top, the blue line is the simulation, the orange line is the way that we tracked the ST elevation, which in my book is pretty damn good, to be honest. So we were really happy with this. And if we then conclude, I think this is a very powerful algorithm. We have been talking about neural networks a lot. And I think the beauty of this one is that it combines a lot of medical and technical knowledge. So we use a lot of knowledge that we have on the ECG and knowledge on neural network design. So it's a very rigid neural network design, which entails a lot of knowledge about the ECG. So it has only few weights, which means it's very data efficient. It was only trained on the data of 10 patients. It's also very robust, basically because you know what's going to do. There's no unpredictable behavior. And to some extent it's also explainable, because you can really explain what it's doing. Of course, there are some gray boxes in between, but the final result, we know what it's doing, what it is supposed to do. It seems to be applicable to physiological and pathological cases. And what we also saw, that it can adapt itself to ECG morphology. And with that, I think it has a strong potential for detection and prediction of, in the end, maybe fetal complications by using maybe ST analysis under non-invasive, so the abdominal ECG. And this work was, as already introduced by Danilo, this work was done by a PhD student in the group, Ivar R de Vries, who unfortunately couldn't be here, so I was giving this presentation on his behalf, but all credits go out to him. Thanks.